In this video, we look at sampling distributions and the central limit theorem. So if you recall in statistics, back at the beginning of statistics, we talked about the difference between the sample and the population. So remember, the population is the entire group that we're interested in studying, and then the sample is a subset of that. And so we often talk about population parameters, values that describe the population. Often we use Greek letters. Mu for the population mean, sigma for the population standard deviation. Now oftentimes it's not feasible to get all the information from an entire population, so in statistics we often gather a random sample and calculate sample statistics from our sample data. So the idea is we use these sample statistics to make estimations about population parameters. So here in Chapter 6 we look at sampling distributions. The idea is to look at the probabilities. How does a sample statistic get distributed across various random samples? So some examples of how we estimate in statistics. X bar, or sample mean, estimates the population mean mu. S estimates the population standard deviation sigma. And later we'll talk about proportions. P hat estimates the population proportion P. So get an idea of what we're talking about here, suppose we have any population with some mean mu and some standard deviation sigma. We may not know what these are, but if we start sampling from this population, what does the X bar sampling distribution look like? It has several characteristics. Number one, the mean of the X bar sampling distribution will be the mean of the original data. Another way to think of this is, suppose we have a box with a whole bunch of numbers in it, and we don't know what the mean is, or we don't know the standard deviation. If I were to start sampling from that box, taking out 5, 10, 15, 20 numbers at a time and calculating X bar, what number one is basically saying is if I were to do this over and over again with sample after sample, that the X bar values would get closer and closer to this mean, or they would be centered around the true mean of the population. Another way that this is denoted is mu sub X bar, the mean of the sampling distribution for X bar is the mean of the population. Second result is the standard deviation of the X bar sampling distribution is sigma over the square root of n. Or again in notation, sigma sub X bar, sigma over the square root of n. And if you think about it, two notes here. If I start with that example, drawing numbers from this box, the distribution of how spread out these numbers are, these X bar values that I'm calculating, will inherently be somewhat dependent on the population standard deviation that we started with. Hence there's a sigma in here. But also if you think about it, the larger my sample size, the more likely it is that X bar will be closer to the true mean. So the distribution or the variation of these X bar values should get smaller as my sample size gets larger. Another way to think of it is if I draw 3 numbers out of the box and calculate X bar, or I draw 100 numbers out of the box and calculate X bar, I'm more likely to be closer to the true mean with the larger sample. So as n gets larger, notice that this sigma sub X bar gets smaller as n gets larger. This is also sometimes referred to as the standard error of the X bar sampling distribution. The third result is the central limit theorem. The central limit theorem is a very powerful result in statistics. It basically says that if I take a large enough sample for means that's generally 30 or more, that the distribution of X bar will be normally distributed or very close to a normal distribution. So what this allows us to do then, if I know X bar has a normal distribution, I can associate probabilities when I use X bar to estimate population means. So if we look at an example here, suppose we have human body temperature normally distributed with mean 98.2 and standard deviation 0.79. So if I randomly select one person, what's the probability he or she has a temperature below 98.5? Well, this would be a simple conversion to a z-score. I would take that 98.5 minus the mean over the standard deviation, get a z-value of 0.38. I would then look that up in the z-table and find 0.648. So about 64.8% of people have a mean body temperature below 98.5. Okay? Here I selected one person. Now if I change this and take a group of people, suppose I randomly pick 30 people from this population and calculate their average temperature. So I ask everybody in my sample what your body temperature is, and I average those. What's the probability that the average of the group is below 98.5? Similar idea, only here I'm talking about an X bar value. So notice my standard error is not just sigma, but it's sigma over the square root of n. So I take that 0.79 divided by the square root of 30. When I look that up in the table, I get 9812, where the probability that X bar, the average of this group, is less than 98.5 is 0.9812.